thank you. Thank you for the invitation. It's really very nice to be here. So I do Fermion Monte Carlo, and I try to select some things which may or may not interest you. I mean, yeah, I don't know, right? Don't look at me like that, right? You scare me right away. That's okay. Just go on. I don't care. Okay. So Fermion. Oh yeah. Good luck. Good luck. Thank you. Good luck. You're the good luck chairman.
Yes, I am.
Okay. So I wish myself good luck. Good luck for me. So let's start. Do we really want to start? No. Okay, we do. Okay. So Fermion Monte Carlo, I'll give you some, some flashes of, what we really do and where I won't talk about the problems. And I have some selected applications which are based on what we heard this week, defects and DQCPs. And then I'll go to some models which are, we heard about the Hubbard model, we heard about the Kondo model. We didn't hear about the SSH model this week. And the SSH model is, I'd like to persuade you that it's a remarkable model which has also extremely interesting physics, DQCP, which you can tune from maybe weakly first order to strongly first order, like maybe the JQ with a QN, as a function of n. So, and then I'll touch on something which is rather new. These are then, so this is based on old work. I don't like this pointer. I don't know why. I can use my mouse. Is that okay? Yeah? Okay, so then I'll talk about monopole-free DQCP, models of monopole-free DQCPs. And what's interesting there is that you have some rather interesting boundary phenomena, and I'd like to talk about this if time allows, right? So don't hesitate to interrupt. Not you, but all the others, etc. So Fermion Monte Carlo, we have a partition function. We can only do thermodynamics. That's all we can do. And we use Hubbard-Šotanovich fields to decompose any type of interaction to a sum of non-interacting system. S of phi is basically an action which is, which you can solve for a given configuration of the fields. And then you'll just sum over the fields, it's high-dimensional integral, and we know that the Monte Carlo method is good for that. So that's the idea. That's all it is. And then, of course, there are many. So this is a formulation. Any two-body Hamiltonian can be written as a sum of perfect squared. So this is a very generic example. You have H0, which would be hopping or something like that, and then a one-body, and then a sum of perfect squares. And well, you just do a simple Hubbard-Šotanovich transformation. It's done here, exactly, right? It's Gaussian integration, and then Trotter, etc. And then this is something where you can integrate out the fermions and get it as a determinant. And of course, the major question, so far so good, is the sign problem, which you've heard about. This fermion determinant is not always positive. And you have to ask yourself the questions, under which conditions will this fermion determinant be positive? And that's not an easy question. What is the most general way of asking, etc., has triggered a lot of research. But the easiest possible thing is to say, well, let's assume that I have time reversal symmetry or an anti-unitary transformation which squares to -1, and then you can show, provided that you have a supplemental U1 symmetry, that all the eigenvalues of the determinant comes in complex conjugate pairs, and you have no sign problem, right? So before starting the code, in principle, you should be able to show that you have no sign problem. And this has allowed us to do a lot of work on models and, before, and to see what type of models we can solve. And I think the class of models, well, I'll leave you to judge it if it's your choice. But the class of models we can do is not uninteresting for me. Okay, that's it. So if we have no sign problem, it's a slow method in the sense that if you have no autocorrelation time issues, you're in a phase where the correlation time does not diverge, then the computational time is the volume to the cube times beta. So it's slow, right? It's slow. So critical exponents for fermion systems are hard. Okay? I think we all agree. And so this is a package we have been working on for the last many years now. And this looks complicated, but it's a very general Hamiltonian, one-body terms, two-body terms, and coupling to a gauge field, which is Z of k. You can do many things. There are internal symmetries, and this is our working horse, and that's what we use. You can see some people here in the audience: Johannes, Emily, Francesco. I have my reading. Here you are. You're all together. Amazing. Okay, good. So here they are.
Yes. I'm sorry. Yeah. But just a very naive question. Can you contrast it with what are other types of, why do fermionic as opposed to bosonic, what are the advantages, disadvantages? Just can you say in one sentence? Or is it just an interesting class of models?
Because fermions are the basic building blocks, right? So I mean, if you want to do Fermi liquids, if you
okay.
Come on, I mean, sorry.
Okay.
I mean, fermions are the. I mean,
so it's just by necessity.
But just by necessity, if you want to do all, I mean, that's my take, right? And the claim is that all the bosonic models which Anders can do, I can do them with the fermions, not as efficiently, but I can do them. So it's a more general approach. Okay. Agreed, Anders?
I guess so.
I mean, fermions are really, I think, would be the. That's the desire, at least, to be able to do fermions in order.
There's, of course, another formulation which is also useful sometimes, where in fact you introduce a lattice in the time direction, but you keep a subgroup of the full Poincare groups here. You're guaranteed to get back to Lorentz invariant.
Right.
Now, I realize not all theories are Lorentz invariant, but in that particular case, I wouldn't use Trotter things because I would want to make sure that it was a Lorentz invariant theory.
Yeah, so from my background is Lorentz is emergent. It's not always there, right? I mean, it's we state. So.
But if you think that's your target, you wouldn't want to use Trotter because this way would build it in as a necessity, right? Okay. And of course, it's not Lorentz invariant. I wouldn't do it, of course. Right. But I'm just trying to contrast it, and then you can do it with the standard sort of hybrid Monte Carlo and so on. So that subset has a better algorithm, I would say.
That's not always true. We tried our luck with hybrid Monte Carlo on different. So it's a competing algorithm. Okay. So hybrid Monte Carlo is something. Okay.
Very similar.
It's very similar. I completely agree. And our package has a hybrid Monte Carlo implementation also.
Okay, good. Right.
But with exact forces. Whatever that means, we don't do a stochastic sampling of the determinant. We can talk about it afterwards.
They're both inside.
Never mind. Let's go to physics. We can spend the whole time. No. We will miss lunch.
No.
Okay, let me start with some selected applications. Right. That's it. That's all I have to do for the technicalities. And let me start with defects. I know defects were important when we heard Max talks, etc. And this is something which we can do. You can just plug this Hamiltonian into our code, and it's rather interesting. It's physically motivated. Right. There are experiments behind this. And the experiments are this, is basically you take a surface, a two-dimensional surface, so explicitly that would be a copper 100 surface. And then on top of this surface, you do you put a small slab of insulating material, that's copper nitride. And then on top of the copper nitride, you put some cobalt atoms which have a spin, actually it has spin 3/2, right? So we're going to do a spin 1/2, but these have spin 3/2. So this is my surface. This is these EDs of S are basically represent my cobalt atoms, the spin degree of freedom of my cobalt atom. And it turns out that in experiments which are here, that there is a direct exchange, a Heisenberg exchange between the S of R prime. So there is a dimensionality difference that's very important. This is 2D, and this is basically a one-dimensional chain of spins, if you want, on the surface, right? So this is something we can solve. It's a Heisenberg. These are free electrons. We can solve this. And then we have a coupling, which is called a Kondo coupling. So it's a S.S coupling between the surface electrons here and the spin, or impurity spin, we call it very often. And so this turns out to be, so this is a typical, I think if you go to Max talk, it's basically, it would be a three-dimensional object with a surface, I don't know where Max is, with a surface height. So with a surface which would get the impurities. So it turns out that these remains metallic states, right? Even if you have particle symmetry, and depending on what surface you choose, if you choose a Dirac surface or if you choose a Fermi surface here, you will have completely different phases. So this one is maybe for people who like Lorentz invariants. This one here, where you have a Dirac cone here, and this is a one-dimensional spin 1/2. So it is actually very nice in the sense that this is Lorentz invariant. This is, of course, by definition, Lorentz invariant. And the coupling may not kill this Lorentz invariance, etc. So the phase diagram of this object is that if you start with this spin chain on a Dirac system, on a Dirac surface, then you can see, just by doing power counting, you'll see that JK is irrelevant. So you go for small JK, you get to a phase where the spins, if you want, decouple from the conduction electrons, right? And so that's the easiest, that somehow has something to do with the Kondo breakdown phase you were talking about, right? But it's a mini Kondo breakdown phase. I mean, it's not the one you would like, but that's the best we can do numerically. And then if you go to large values of JK, then this will be, the spins will be screened and you have a quantum phase transition, which could be studied, right? I mean, it's a Lorentz, we believe it's Lorentz invariant, et cetera, which could be studied in more detail. We haven't managed. All we have for the moment are the very clear signs of the two phases. Then there is this other case, which is, I think, even more interesting. Well, it's different, right? And this is now a Fermi surface, so you break the Lorentz invariance, and as Max said before, we were rather surprised to see that if I put a spin 1/2 chain on this type of surface, then if you look at what happens to, is this JK irrelevant, marginal, or irrelevant, then it turns to be marginal. And Manuel Weber basically did some very, very nice simulation to show that it's marginally relevant. And what happens is that because of dissipation, essentially, this spin chain becomes long-range ordered, right? And then so you have a small JK, you have long-range ordering along the spin chain, and then when you go to large values of JK, you have exactly the same phase. The large JK phase, where the spins are screens, are independent of if you have a Dirac cone or a Fermi surface. So I think these are things you can do, and a lot of edge physics or defects can be done and can be compared to different methods.
So you mentioned it's long-range ordered if you have Fermi surface, right?
Yes.
So is it easy to distinguish this long-range order from the extraordinary log of max? I mean, in the max.
It's a long-range ordered phase, the extraordinary log. This is really a long-range ordered phase.
But
in practice, you don't. It's a z equals. It has a different dispersion, right? It's the dissipation. The dissipation is the phenomena which allows you to stabilize the phase. So it has a different dynamical exponent. I don't think it's a Lorentz invariant phase. So I think it's different.
Max?
I think because here you have a Fermi surface, right? So it's not embedded in a conformal field theory.
Right.
So
it's a bit of a different.
The arguments that were given for long-range order along the chain, they're kind of Hertz-Millis type arguments. Right. But okay, this is the best that we have right now.
So that's it. So this is a slide on the defects, just to tell you that you can do that right here. Then there's another part of the applications, which is DQCP. And DQCP for me is basically, I always start with fermions because we do fermions. And the way we understood this is we would like to simulate this Hamiltonian. This is really the Hamiltonian of graphene, where we did a transformation to explicitly see the SU4 symmetry, as Igor was saying in his talk. And so this psi here is an 8-component spinor, where you can add words to these labels. These are two entries. So this would be, I don't know, sublattice, valley, and spin, for example. So this you can really see the SU4 symmetry. And you have, for this choice, you have a quintuplet, many actually, but you can just, one possibility, a quintuplet of anti-commuting mass terms. And this quintuplet would be mu z, and then you have tau z sigma. These are 3, tau x and tau y. And then you can see rather easily that this is, this is a very high symmetric Hamiltonian. It has Lorentz symmetry. It has SO5, this SU4 symmetry, which is broken down to SO5, et cetera, et cetera. So this is, of course, a candidate for the DQCP, the deconfigured quantum critical point, from the perspective of fermions, if you want. And the question is, can we simulate this, right? And so also I want to say, if we integrate out the fermions, then this will lead to a level 1 Wessel-Witten term, as we saw, I think, already this week. So before meeting Mike at a conference, I had no idea how to do that. We had no idea how to do that. And now it's becoming sort of mainstream, I guess. But the key thing is to find a regularization. So if I try to take this and put this on a lattice, then I'll break all the symmetries. I'll break, of course, a Lorentz symmetry, and I will also break the SO5 symmetry. There's no way I can do that. And so we have to find another regularization. And what was proposed some very, very long time ago now was to use the Landau levels, but on a torus. We did that at that time. And so I'll go quickly because I think you know all this. I mean, stop me. This. If we take the paper of, one of the papers of Subia, we can see that this is, maps exactly onto what we would like to study, and we can do the simulations. Now the simulations are not so easy. If you have to have Mike's knowledge, in my opinion, at least not mine, to show that you can use a fierce identity to replace this term by this mass term, if you want, by a tau x, a tau y, and a tau z, right? with some factors, and these factors are very important, and it will tell you that you will be able to simulate this model for values of u0. u0 is the magnitude of the SU4 term, u0 bigger than -1. Now, it turns out that the computational time for these models in this version of this old version is extremely expensive, because when you project onto the lowest lambda level, your local interactions become non-local, right? And so that you lose a factor of volume because of that. And then it turns out that you lose another factor of volume if you want to get the Trotter decomposition working well. Normally we do Trotter decompositions for local Hamiltonians. Now you do a Trotter decomposition for a non-local Hamiltonian, you have to be very careful, and you lose another volume factor. So with this, we could do simulations up to 100 fluxes, right? So it's much larger than what we saw for the fuzzy sphere, but maybe the truth is that we can get less out of it than what you can get. So we're very jealous.
Can you work in continuous time?
In continuous time. I don't know how to do that. You should ask Emily. You know, the continuous time we know are basically these for very special cases where you can elevate things and, you know, the interaction to the 4 is the same as the square, blah, 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 blah. That's not the case here. So if you could do it, it would be nice. You would save, I completely agree. I just don't know how to do it, right? And so what we've done is we're working still on this with Ziyang and a lot of people. Yon Chen, who is here, is also and to find some better algorithms. We can gain a factor of volume by doing some better updates, right? So that is possible. So we can continue. We'll continue on this. Now, to cut a long story short, what we have for this model up till now is, well, you know, if you just look at the results and you did not have any background history of DQCP and how complicated it could be, you would get to the wrong conclusion, right? So as a lot of us did. So this is just to test. We have a Fermion model. We would like to be sure that it's insulating. So we look at the charge, the fluctuations of the total charge as a function of temperature, and indeed it goes to 0 exponentially. So we do have insulating states, just to be sure about it. That's good to check. And then what we do to see if we have long-range order or not is to look at those SO5 correlators. So M is a 5-component vector of the 5-component order parameter vector, and we calculate the correlation functions, and essentially we calculate this RG invariant quantity. If I have an order at Q0, then this will go to 1. If I have something which is disordered, when delta Q goes to 0, this will go to 0, and at the critical point, it's something which is a constant. Okay, it's an RG invariant object. And so these are the best results we have, as I say, up to 100 fluxes. And you see that if U0 is very big, then this goes down and turns up, seems to go to 1. So we have an SO5 ordered state. And then if we go to lower values of U0, then, you know, we don't really know. This is going down. Maybe that there will be a length scale where this will turn up and go up again like this, or there's something critical. You can do a crossing analysis, right? So you see that we could come up with a crossing here at a given U0. There could be a crossing, and you can decide it's maybe not a very good crossing, but at least there's a crossing there. So with this, you know, up to 100 fluxes, right, which is big, we can go up to 150 now. Then the conclusions are slightly depressing, right? We can say that we have an ordered phase, right? Well, I'll take the word depressing away. An ordered phase, and the other thing is that, well, at small u0, the correlation length is bigger than our system size. That's the two things we can conclude, right? And then you have many possible, interpretations, etc. You know, you could have a SO5 CFT, which seems to be now, I mean, if we look at Wei's talk on Monday, maybe seems to be excluded, etc. And one easy way out, at least, is to say, well, you have a fixed point collision here. These 2 points, you know, they collide and go to a complex plane, and you have some type of walking scenario here, right? And that was talked about many, many times, I think, this week. And of course, there's the tricritical scenario of Anders, which I'll touch upon later on. So if this is the result, I mean, so this motivates my other part. If this is the results, well, you know, at least from a model perspective, you could bang your head against this and try to get to bigger and bigger lattices. The other thing you could do is to say, well, if this is the case, then I could always find models, if you want, where the models can be here, so I will flow very slowly here. Or I could find a model which starts here, which is very strongly first order with the same symmetry, right? So I should be able to find models where I can just tune the criticality, right? That's what we are trying to do. To a certain sense, it's already done, right? By Anders, you agree that the range of your interaction does this, right? So
yes, but I was going to ask actually, can you not put something in this model which would tune the strength of the first order? Or?
So we did it with maybe I'll come back to this question at the end, right? I think I know how to do it, but we just do it. So this what we have is tell you what to put in, okay? And then we can put in all the models, in my opinion. Okay, so
in this model, do you have SO5 emergent?
No, SO5 is exact. So what you break, so the Lorentz symmetry, the projection keeps SO5 exact, it breaks the Lorentz, right? Correct? The projection breaks, yes, the Lorentz symmetry, but you have SO5 exact. So you're exactly on the SO5 line. There's no emergent SO5. Okay, so should I go? I'll go on. So this is the thing of the SSH model, and these are the people who really worked on this. Annika is the person who did most of the work, really. She's amazing. She's just carrying out her PhD now, and she's sick and tired of physics, and she stopped. Happens, right? Well, I'll take it back. I'm being recorded. She won't watch it. I know that. She won't watch it. But if she doesn't, but she's very, very good. So Annika, you're very good. You should continue. But here it is. But if she doesn't want to, what can we do? That's it. So this is the SSH model, and it's one of the, I believe, one of the many body classics, right? Alongside the Hubbard model, I would say. And so this is, what is it for people who don't know? Who doesn't know the SSH model? Okay. Good. So that's it. And so no, really, it's really very simple. It's embarrassingly simple. This is like the Hubbard model. This is just a tight binding, a square lattice in our case, right? You can hop, and essentially the hopping can be direct like this, or it can be we have a bond variable which can oscillate. That's what we call a phonon, because it's a harmonic oscillator which will modulate the hopping, and these is what you call Einstein phonons, in the sense that you have independent harmonic oscillators on each bonds. That's it, right? That's it. Now in 1D, this is an amazing model. And you have, in 1D this Zoo Schrieffer-Heger. Yes. Okay. It's been Zoo Schrieffer-Heger. It's a model for solitons. For the easiest possible topological insulator is included here. And then you also have some unconventional quantum criticality. This is work, again, by Manuel Weber, Martin Hohenade, and Francesco, who's in the audience. This is a beautiful work that those three people did. In my opinion, is as a function of the inverse frequency here as an electron-phonon coupling. This is a one-dimensional quarter field. So if the electron phonon coupling is not very big, you have a Luttinger liquid. If it gets big, you have two types of possible symmetry breaking, which correspond to two Dirac masses. One is a tau x, which would be a bow, a VBS state, and a tau z, which would be a charge density wave. These are symmetry different because of parity. And if the Luttinger liquid parameter gets bigger than or smaller than a half, then you have a direct transition, a continuous and direct transition between these two states. And exactly at this point here, you have a emergent U1 symmetry with a Luttinger liquid. So this somehow can be classified as a one-dimensional version of a DQCP, right? There are other versions in 1D where you take different mass terms, the three antiferromagnetic mass terms and the bow mass term, and that's another form of DQCP in 1D. Okay. So this is the motivation, and the motivation. Can we do this in 2D? In 2D, all the physics we've seen in 2D for the SSH model did not have this exotic flavor, right? Which I like. Point, right? That's it. So what we're going to do is add something to this model. So we're not going to take exactly this model. We're going to modify it. And we're going to modify it for various reasons. So the modification here is I take this hopping, this term which is here, and I just put it to the squared, right? So for me, I'm allowed to do that because it's symmetry allowed. I don't change any symmetries of the model. It's a term that will be dynamically generated, right? So I'm allowed to put it in. And it allows to do some technical tricks. I won't go into it, but to allow us to integrate out the phonons and to get much more efficient simulations. And this is based on a very nice idea by Sandro Sorella and these people in this paper. So by adding this term, we can get a much more efficient algorithm, and the claim is that we don't change the physics. And it also allows us to tune the DQCP, which we will see. So let's start with some symmetries of the model. First of all, it's very high symmetry. This was touched upon, I think, by Igor. I mean, you can, this is, in principle, you start with an SU2 symmetry, but actually, if you write this in terms of Majorana's, you have a O4 symmetry. So it takes Majorana's, a Majorana form for different for the A and B sublattices, and then you can really write like this. You see, basically, you have bilinears of Majorana's. Sigma n here are always diagonal. So you have an O2n symmetry. Now, we will, I mean, to be sure about what we're doing, we will want to break this symmetry to go back to the symmetries of a JQ model, for example. And to do so, we would like to go from O4 to SO4, and what we will do is put in a fermion parity operator, which is nothing but the Hubbard interaction for us. And this is the product of the 4 Majorana fermions, and that is, you know, odd, that transforms in this way. Okay, so it has an O4 symmetry. Everything which I will tell you is remains valid if I break this O4 symmetry down to SO4, and that would be the symmetries of the JQ. Right. Okay, now there's another point which is where that's the point where the model becomes where you have emergent Diracs. That's a key point for us, and this is the point where you here you can talk to your solid state colleagues and they're still happy. And then here you stop talking to your solid state physicists because you put t equals 0. And so this is not an electron phonon model anymore. It's something like an assisted hopping model, right? Okay, but it's valid from the model point of view. It's valid. And then in this limit, when t equals 0, you see that you have a local Z2 symmetry which comes out. And I think for this audience, it's easy to see, is that essentially if there's a fermion on this center site here, if I hop out of this site, then I will change the parity on this site. But because I only have assisted hopping, if I hop here, I will have to absorb or emit a boson, which are these A's, right? This is this term. So essentially, it tells you that the fermion parity times the sort of star operator here, basically the parity of bosons on these 4 links here, that's a locally conserved quantity. Okay, so it's what we called an unconstrained Z2 gauge theory because we're not going to impose any type of gauge constraint. We're just going to do the simulations over the sectors, the Z2 sectors you would call them.
Gauss law sectors or something.
The Gauss law, that sounds much more better. So under the Gauss law sectors, Uwe tells me to say this, I'll say this from now on. So what does it mean? What does it mean is that it means that if my fermion is actually my fermion becomes an orthogonal fermion, right? That's what follow this paper, right? This is the simplest, I forgot the title of this paper, but that's where they introduce orthogonal metals, Max, right? And so this because this has a Z2 gauge charge, this won't move, right? So if I calculate this correlation function, it's going to be local in space, but it's not going to be local in time because I'm averaging all of my Gauss law sectors, right? And so you can see this numerically, right? If you just don't realize what's happening, you put your t going to 0, and you calculate your single particle spectral function, you'll see that it's completely k independent, right? That we see. The fluctuations here are basically people who know Maxent, the issues of Maxent, right? So this is another thing which is important for me is the gap, right? There's a gap here, and this gap here is basically the gap between the ground state, where the ground state, the sector of the ground state, and the first excited state to the different Gauss law sector. Is that okay? Okay, that's it. Okay, that's it. So that's the point. So that's important because this gap will tell me that this point is not singular. So I'm looking a bit ahead. So what we have to do is to find some type of operators which are gauge invariant, and to do that we follow this paper of Manfred about basically Z2 slave spin theory. And what we do is, the fermion, we write it as a type of a Z2 gauge theory, which carries the Z2 gauge charge, and this is a real an electron. The constraint for this is this, because we have too many degrees of freedom. And we can also define a boson. The boson also carries gauge charge, and so this B here is a boson which is stripped away from its gauge charge by these taus. And if we do that, we can rewrite our Hamiltonian in nice ways in terms of gauge invariant object. These are these Fs. These are real electrons now, etc., and everything stays the same. And so we can measure gauge invariant objects. We cannot. We don't know how to measure this, right? Because we don't have access we have only access to this in the code. We don't have access to this quantity directly, at least. We can measure the flux, right? What the flux felt by these F electrons here. We can measure dimer-dimer correlations and spin-spin correlations. So the key point is the flux, right? What happens to the flux? And it's not a surprise because of one of Lieb's papers that you will get a pi flux. So this is a numerical simulations at given parameters, and you look at the flux as a function of omega 0. So we change the phonon frequency and look at the flux. You see this is all blue. That means it's all negative. So we have a pi flux, and we have essentially generated Dirac orthogonal fermions.
So I got a little confused.
Yeah,
so
sure.
You're simulating that model right there.
No. Yes.
Written on the top.
I'm simulating, yes. I'm simulating
And
this.
the F's are gauge invariant or not?
These ones are gauge invariant, right?
These are gauge invariant.
These are gauge invariant, yeah. So these are not gauge invariant, right? So it's a bit, how you start. These are not gauge invariant. The C's are not gauge invariant. Then I change my C to tau times F. So tau is
I don't see any difference in the two Hamiltonian.
Yeah, you don't.
there are nones. Because all I'm doing is I'm putting a tau Z of I, tau Z of J, and I'm absorbing this into a redefinition of the boson.
So what's the point?
The point is to show that I have to think in terms of my orthogonal fermions and not in terms of my fermions.
What is the object which feels the flux? It's the orthogonal fermion. It's the fermion.
Okay.
That's the only point.
I mean, the C
The F fermion. The F fermion.
The F
But
fermion.
since there's no difference in the Hamiltonian,
Well,
oh, you're saying okay.
there is a difference because if
There's
I
a spontaneous
yeah
flux that appears.
there's-
Okay.
It's a spontaneous flux that appears.
All right.
Okay. Thank you. Should I go on?
Sorry, I was confused
Yeah.
by color code. So you have two color codes?
So this is the Monte Carlo result, and this is the color code. So I see that as a function of frequency here for this parameters, I always have a pi flux. That's the only message I have on this slide. Pi is negative. Pi is negative.
Sorry?
That's a weird sentence.
E to the I pi is -1.
I agree that it's negative. I agree that it's a weird thing to say. I agree, but we say it in the group all the time.
You see pi or 2 pi?
We see pi.
Because E of I2,
This is from the color code.
because it's negative.
But I mean, negative numbers there. There's -2.
Listen, here's what we measure. Here's what we measure. We measure the product of x around the plaquette. Right? So I go around the plaquette. I measure x, 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 x. I get a negative number. Right? Which essentially means that my electron, my F electron, acquires a pi phase. No. It's a pi flux, right? The fermion's already a fermion there, right? No. Okay, so this is one electron. Okay, is that okay? So we have a pi flux and we have Diracs. That's it. And so so what I want to also, so we've done a lot of things in the t equals 0 sector, right? In the t equals 0 sector, and then we'd like to change, we'd like to go away from t equals.
What is the phase diagram of this?
Yes, I'll show you now. Just bear with me. I'm trying.
Okay, go ahead. Go ahead.
The phase. Okay, go ahead. So before coming to the phase diagram, I'm sorry, I'd like to be sure that you agree that because I have a gap between the different Gauss sectors, then adding up a t is not going to be it's not going to trigger a phase transition. Right? That's the message of this paper. If you don't agree, tell me. I'll be very happy to discuss this. So this is the flux phase diagram. You see that we have these pi flux or Dirac fermions over this whole range here. And if you go to very large values of t's for these numbers here, which I get, then you go back to a 0 flux, to more like, I don't know how you say it, just a full Fermi C, something like that. And the phase diagram is this now. This is what we have. Then in this domain where you have these emergent Dirac fermions, you do have a pi 0 VBS and then an AFM as a function of frequency. That's in this domain where you have the pi flux. So I have to be a bit careful here. These are simulations where we scale beta and L, which is fine if you have Lorentz invariance. You will, when you go away from this flux phase, if you want, this pi flux phase, you will lose a Lorentz invariance. And then the beta equals L is actually a high temperature, right? So this phase is actually a pseudo-gap phase of a much lower, if we just keep beta equals L, of a pseudo-gap phase of a much lower, if you reduce the temperature, you will get a pi VBS. So this is finite temperature, and this is representative of the ground state. Right? That's the way you should read this diagram. But I'll talk about this. Okay, so that's the answer. That's the yes.
Pi 0 VBS means it spontaneously breaks rotation.
C4 symmetry. Yeah.
Either pi 0 or 0 pi.
It's pi 0 or 0 pi. Yeah. So that's really things like that. It's fourfold degenerate.
Good.
Right, with translation and rotations.
So in your phase diagram, there's no like Dirac coupled.
No, we didn't find that for the moment. So we did not find, in principle, it's a very good question. We did not find that a Dirac spin liquid or Z2 spin liquid. We didn't find that for the moment. Right? So not in this model. And so this is what we. So this is the DQCP we see, and well, the pseudo criticality. I don't know how. So these are the results. It turns out that this. So these are correlation ratios for the dimer and for the spin. And if you look more carefully to this, you'll see that the data is not so good. There's a lot of crossings, right? So there's a lot of drift, right? So it's hard to get anything out of this. So we had to go, to scale down and see, what are the minimal requirements I need to say that I have a quasi-criticality or something like that. And we went back to dynamics, right? So this is again the single particle telling you that we're very close to the Z2 limit. So T is rather small here. It's 0.1 actually. I didn't tell you this. So we're all doing. Yeah, it's actually here. It's this line here. The 0.1. This is the VBS dynamics, right? This is the spin-spin dynamics, and these are the histograms for the VBS order. So if I start with the histograms, you see that as Anders did a very, very long time ago, Adam also. You'll see that more or less at the critical point you get this nice emergent U1 symmetry. The other thing we can check is emergent Lorentz symmetry because our model is not all but Lorentz symmetric, at least what we put in the computer. And you see that this is the velocity of the VBS. This is the velocity of the spin. So there are different scales, but actually these lines have exactly the same slope, right? So we have the notion that there is something like an emergent Lorentz symmetry and an emergent U1 symmetry, and these are the two things we're saying. We'll just call this, it's a very poor man way of looking at DQCP compared to the very sophisticated things we have seen this week. So I apologize for this, but we can't do better for the moment.
Fakher?
Yes.
This emergent Lorentz symmetry between the order parameter
Yes.
and the Dirac fermions, is that difficult to get? Do you need a certain size of the lattice?
No,
to
this is a
convert
small
okay.
size. This is 14 by 14.
Do you get this right away?
You get it pretty much. On this scale, you get it pretty much.
Do you understand why?
No. How do you know how I should do you have an idea of how we could understand
The
it?
order parameter is something that should be dynamically generated.
Yes,
somehow.
it is. Yeah.
So at the beginning, it doesn't know about the
Yes,
Fermi
exactly.
velocity. So
Yeah, it's a thing we're using more and more. Every time we have a suspicion of a model who has a DQCP, that's the first thing we look at now to see if the Lorentz symmetry is there on our small lattices. And it turns out to be it's a good tool, put it that way.
yeah, it's cool. I like it very much.
So that's what we do. That's what we do. Okay, so now about the tuning. Now we have this lambda thing here, right? We have this lambda here. And essentially we can change this lambda. And you maybe know that if you take this for SU2, if you take this this operator and you do the calculation, you will get spin SI dot SJ plus, because you have O4 symmetry, eta dot eta. And eta are, how do you call those etas? They are the particle transformed of the S. They are Anderson. Sorry?
Cooper pair?
Yeah, the Cooper pairs, right? The Cooper pairs operators, right? So you have S dot S plus eta dot eta. And so this term will, if you make this lambda bigger, then you will make this AFM phase bigger. That's the idea, right? And if you make this AFM phase bigger, then the critical phonon frequency at which you will get this DQCP should go down, right? And it does. So this is the plot. So these are basically d of f over d of omega 0 this is the data I was showing you before. That was for lambda 0.5. That looks something like smooth. And if you go to lambda 1.5, then you really see a beautiful jump, right? And so that's very strongly first order. You can, on these small lattices, you have some hysteresis, right? So this is a hysteresis for lambda 0.5, and you don't have it at 0.5. Now, believe me, you can do the same thing. These are the histograms. Now, this is the histograms which tell us you have a DQCP, and this is histograms where it tells me there's no DQCP, because you really see those 4 points here, they don't go to. I mean, there's something in the middle which emerges, and here they just disappear like that. So there's no emergent U1 symmetry at lambda 0.5. On our small lattices, we would have an emergent U1 symmetry here. Okay, so that's a very clear sign of, I mean, the first order is very clean. If this is continuous, I don't know. Okay, and so just to tell you to be...
Shouldn't you see the radius of the circle shrink? Is that what?
Yes, the radius of the circle that shrinks and gives you some type of something symmetrically or circle, that's the signature of the U1.
Yeah, right. I mean, you get a U1, but that doesn't imply a DQCP.
No. It just tells it's one of the conditions. If I don't have this, then I need the emergent U1. Right.
So this U1 symmetry is dual to the emergent U1 gauge symmetry of polygon.
But so to get a second order phase transition, this radius should shrink to 0 at the critical point.
The emergent symmetry is actually dual to the absence of monopoles in the CP1 formulation. It's quite normal. I don't think well, maybe you know that already, but yeah, it's quite different from the usual.
This I know, but
did he answer the question?
I can talk to him afterwards.
Okay, it's other one. It's very useful to have public which answers the questions. It's really nice. I like you guys. It's really good. So this is just to tell you that since we were very worried about symmetries, rightly so, we did all the same calculations with adding a negative. We could ask positive or negative. You don't really care in that case. Hubbard U to go from O4 to SO4, and you can go through the data, etc. But we really see the same thing. Okay. So what is the interpretation? The interpretation is unfortunately, as always, there's nothing unique. So essentially, this is the phase diagram I showed before, and well, this is the short. I went too quickly here. What is essentially? When you have phonons, when you integrate out phonons, you have a retarded interaction in time, and there's a length scale for this retarded interaction, which is 1 over the phonon frequency. Okay, so when we change the lambda, right? When we change the lambda, essentially, when we change the lambda here. Essentially, the phonon frequency at which the transition happens goes down. Not by much, but it goes down a bit. And so you should see this as a set of models with various range in imaginary time, or in real space if you buy into Lorentz invariance, at least close to the critical point. Okay, so you're varying the range of the interaction. And by doing so, you're basically moving along this line, right? So here, this is a short range model. This is a long range model. I can continuously tune here. Here, it's strong first order transition. Here, I have to flow very slowly. It's a very weakly first order or something else. At least I don't distinguish it, right? Other possibilities are the Anders multi-critical point. Could very well be that here is the short range. Here's a long range. So that would be like the JQ line, which Anders have. I mean, Yin-Chen's question, can we get a spin liquid with that? I don't know, with that model. But according to Anders and Subia, this is no way without a sign problem.
And what about...
I believe you, I don't know. But who knows?
In your case, it doesn't have sign problem.
No, it doesn't have problem, but we never saw this phase. So we will have to go and hunt for that phase.
I mean, I was making the assumption of it's a particular spin liquid that's found in the J1 data model. Right. Who knows? There could be other Z2 spin liquids which are...
So at least we have the potential to hunt for that and see, if we can find something.
I mean, in the proposal, Subia's proposal, that this spin liquid is really just Dirac.
Right.
That what you, in principle, can have easily, right?
Right.
Dirac couple.
Yeah, but we still have, okay, that's true. We could have just a Dirac. That could be a possibility.
Okay. Can't you make quite your lambda Dirac and break gauge symmetry down to Z2?
Right. But he has those.
I don't have a strict Z2. It's a bit fuzzy.
That was a bit fuzzy.
It's not as easy. We've broken. We don't have a t equals 0, so we're a bit away from that. Yeah.
So tuning lambda to be larger made the first order transition stronger, right?
Yeah.
So I think basically like trying to get to the
yeah.
liquid.
So we have to do some. So we have to continue. Maybe do lambda smaller, right? That's what
yeah, or negative even. But would that
negative won't work. That may be the
would that be the
will make a sign problem. So maybe that's exactly where. So Anders is smiling in the back and haha, that's where the critical point is. Could be. I don't know. But we can play a bit around with it.
Okay.
That's all. So unfortunately, this is not the only possibility, right? Because we put in phonons, and there's been a recent paper by Joseph, Orban, and Johannes, saying that, well, if you put in phonons for U1 compact spin liquid, then basically there's going to be a coupling to single monopoles, and that will be relevant, and that will mess up your whole DQCP, right? That's the message of the paper.
Right? Quasi-static phonons.
Yeah, but it's a parallel instability. So that is quasi-static. I mean, I can't exclude this. You agree? I can't exclude. I can't.
The precise statement is that if you have a rectangular lattice or something, if you actually explicitly break the symmetry of a VBS, yes, you
sure. But it's okay. Let it be. That's what they claim, right? In this paper, it's not. I mean, I'm not going to discuss their results. I mean, that's a paper which is out. The key point is that we don't care about this because we can do models without monopoles, right? So we can do exactly the same thing by looking at DQCPs without monopoles, and we get away. We can put phonons in them. I'll talk about this. We can put them phonons in them and continuously change the range of the interaction and not run into this potential problem, right? Okay, that's the key.
So aren't their phonons quite different from your phonons? Because your phonons are like locally gapped modes.
Yeah, but when you couple the phonons to the fermions, you get an emergent dispersion. It's a bit hard, right? To say they stay gapped. It's hard. They can condense at one wave vector and generate some instability.
There isn't a symmetry difference.
Okay. I don't know. If you say that our model does not fall into this possible category, I'll be very happy. Right. Okay. So now how much time do I have? This is. I don't know.
Let's say 10 minutes.
Officially, it's lunchtime, right? Okay. So let me go on quickly. So this is the result. We have this. So two things. We have this Holstein model, which I think has a whole parameter range where you can see a lot of exotic physics. That's the first point. Then it gives you a very natural way of looking at. You have emergent Dirac fermions. You have DQCPs, and you have a very natural way because of the retardation effects. If you want to have a very natural way of tuning things which are rather appealing, I think. Okay. So that's the first part of the thing. Now, what I'd like to do now is to talk about boundaries. This is very new, and I don't know so much about it. And I'm learning every day. But I'd like to start with a model to review some very old results on a model of a DQCP. So this is the model monopole-free DQCP. So let me talk you through this model. Now I'm working on a honeycomb lattice. So these are Dirac. This is a regularization of Dirac fermions. And then just bear with me. I wanted to do this slide a bit better. Forget about this squared term, right? And forget about this sigma and do a sigma z. So this is what you should never do in class. You should always add everything, right? So this would be a sigma z, and this is no square term. And then you agree that that's the Kane-Mealy model. The Kane-Mealy model, it's a topological insulator with a sort of a Dirac mass with different signs for each spins. So the only thing we do is basically to restore all the symmetries of the Dirac fermions. We basically put this as a vector now. So this is a vector, and we square. Right? This is our model. Okay? And this comes out of the blues, but it does what we want it to do. And to do this, we're going to measure an SO3 order parameter, which is going to be this object. It transforms. It's under time importantly under time reversal symmetry. It's even. It's invariant under time reversal symmetry, but it transforms as a vector under SO3. And we're going to see that we get an S-wave superconductor. So that's we're going to measure this. Now the phase diagram of this model is pretty amazing. Is that you start from a semi-metal, you prop up the lambda, you go through a dynamically generated quantum spin Hall state with Goldstone modes, and then you have a quantum spin Hall to an S-wave superconductor. And if you think in terms of Dirac masses, then this again falls into the category of DQCP in the sense that quantum spin Hall and S-wave superconducting masses are compatible. And so they're very nice papers of Tarun, Sentil, etc. I don't know on this. So this is a realization of an old idea, I think. I mean, that's the correct way to say it. And I won't go through the details. One thing which is very important, since we're always working with fermions, is that the single particle gap is opened, right? The single particle gap, these are real fermions. This is the fermion gap, the single particle gap opens up here. This is then an insulator, at least single particle insulator, and this is the single particle gap here doesn't close. Okay, so that was quick. So we just have a model which has these three phases. Just think about it this way, and you can forget about the model now, right?
And quantum spin Hall has an exact U1 symmetry broken.
It has the model has an SO3 symmetry, and it's broken down to by ordering to U1. This is the model. This is what we simulate, Sylvia. Okay. This has an SO3 symmetry.
Okay.
So this is a vector, right? This is a vector because I have 3 Pauli spin matrices which I square to, So it's a vector scalar product of vector, and this vector transforms, right?
I got it.
You got it? So it's a.
And there's also charge conservation. That's the
the charge conservation, the U1. Sorry, the U1 is a charge conservation. I got it. And because charge is conserved, I don't have any monopoles. Okay, so this is the monopole free. Fine? Okay, thank you for the question. None? Sorry?
I was slow.
Yeah, don't tell me you're slow. I mean, I won't believe that. But so this is So this is the single particle gap. So now let's look at this in terms of edges, right? And so let's start with the easy thing. That's a dynamically generated quantum spin Hall insulator, and this object has a pretty sexy name, which is called topological mod insulator. I didn't give that name, but this name is here, right? And so the difference of this has an edge state, but it has some Goldstone modes in the bulk, right? And it's not such. That's not the interest. Well, it's fun, but it's not. What for me is more interesting is exactly this DQCP, where you would have an emergent anomaly in the way, and so that would be an instance, if you want, of what Ashvin and these people called an intrinsically gapless topological insulator. And the anomaly which we generate is because because we gap out the single particles. Essentially, by gapping out the single particle, you reduce the UV on the lattice. We have an SU2 times U1. U1 is charge. And by gapping out the single particle excitations, basically we pin the parity, or the 2 pi rotations, we pin the parity to 1. So we get basically something which is like SO3 times U1, and this has an anomaly, has an emergent anomaly. So we would expect to see some non-trivial edge physics here. Okay, so that's my claim is that the edge physics of this model could be interesting. So these are the results. And this is work which was really Yuhai Liu, who is in Beijing, who's doing all the calculations. And to see this, we placed our system on a cylinder, right? And look at the zigzag edges of the cylinder, and look at, this is just the single particle spectral function in the bulk. So we have just one momentum, which is now well defined. And we can do that in the bulk, or we can do that on the edges. And you see that in the quantum spin Hall, at the critical point, that's the DQCP, and in the superconducting phase. In the bulk, we have a gap. And then on the edge, quantum spin Hall has a very well-defined edge state. So this will be a helical edge state. And we see still a very precise, a very bright edge state exactly at this lambda c, I mean, as close as we can see it. Right? And then in the superconducting, because you break the U1 symmetry, then you will get some backward scattering, and you'll get a mass term for these helical fermions. So the question is, what can we? That looks nice, and we've been sitting on those results for some time because it's hard to get much more. It's hard to get things out of it, and so that's not. So now you have to. This is the experimental part of the thing. So let's start with the easy thing. The easy thing is the quantum spin Hall. I told you that this quantum spin Hall comes out from a spontaneous SO3 symmetry breaking. So you have the Goldstone modes, and this is if you remember. My J operator here, I can't go so quickly. If you remember this, so what we're measuring is the dynamics of this operator, and we see Goldstone modes here. That's not a surprise. Here are my Goldstone modes, right? And then the question would be, how do those Goldstone modes interact with this edge state, right? And I mean, so just by symmetry, you'll see that the coupling, if there is one, of course, but it's very high, in the sense that the Goldstone modes, they are even under time reversal symmetry, and I need something odd under time reversal symmetry to do some spin flip scattering over the edge mode. And so, you know, the high, you can couple still, but the coupling you will get, you can argue that it's irrelevant. So these Goldstone modes in the bulk, they really do not couple at all to the, at least not in a relevant way, to the quantum spin, to the Luttinger liquid. Okay, so that's the easy part, I think, of the thing. What's harder is to understand what happens exactly at this point. And there's a very nice paper, there's at least a conjecture from Chong and some people with him. And essentially Chong did a, so I mean, I'm not sure I understand all the details of the paper, but he basically does a slave particle approach and basically writes the fermions in terms of a SU2 boson and a fermion, right? And the claim is that exactly at the critical point, right, at this critical point, there is a jump in the scaling dimension of the fermion, right? So essentially, at the DQCP, the fermion would be a convolution of the boson and his gauge fermion, right? And then if you go into the quantum spin Hall phase, the boson is Higgsed, and then the fermion becomes the electron, right? So that's what I get out of the paper, and maybe you will correct me, but that's what I get out of the paper, and that will tell you that we'll have some jump in the scaling dimension of my one particle excitation on the edge. Okay, so that's it. And the only thing we have for the moment is to try to come with a proxy for this. And what we do is we measure, so what we really do is we calculate the Green's function in Euclidean time at tau equals beta half, and we multiply it by beta, right? Now, if you work what this means, it basically means that you're taking your spectral function, A of pi omega, and you're integrating it over a window beta around the Fermi energy. That's what you do, right? And so that's the quantity we look at. And this quantity scales as beta 2 minus alpha if you care to assume that your A of pi omega has a branch cut like you would expect in a Luttinger liquid 1 over omega of alpha. So essentially this quantity somehow picks up the scaling dimension of your fermion. And these are the results, right? These are the results. There's no manipulation or anything. We just calculate this, multiply by beta, and plot it, and this is what we see. This is the experimental part of numerical physics. We see this, that it goes up here, here it stays constant, and here it goes down. That's all, right? And so this plot would be consistent with this jump.
But the jump is 1 or?
No, so the jump is 1 and the large n. Yeah. So it's a large n calculation. This is n equals 2.
And what was the jump of your results?
We don't dare to do that. We don't dare to do that because I would have to extrapolate, etc. So we just see that there's a jump, and that we're already happy that. So I think there's much more to do. This is just we're still working on this, and with this I think I'll stop. And just to tell you that another thing which I think is really interesting is this is complicated somehow because this is an interplay of topology and boundary this is the interplay of anomalies and boundaries, etc. So I think it's a very rich subject which I'm just starting to appreciate. And so that I'll stop right here, and then thank you for your attention.
So we still have time for some questions.
Can we go to the DQCP, one of your last DQCP pages, where you had this SSH model and you put it on the RG flow diagram? Yeah,
yes,
the previous one.
This one.
Yeah. So can you comment on the diagram on the left? Is it still loud in your opinion? How would you?
Well, I think yeah. So the diagram on the left is a bit tricky for me to understand, right? Because if I have such a fixed point here, and I move a bit, I tune everything to stay on this SO5 line essentially. If I change a bit things around, then I should always flow back. Yeah. And the question is, what is a bit, right? Of course, if I massively change things, then I can go somewhere else, right? But then I would have to go through another critical point to get to the ordered phase. something like that. So I think that
has anyone seen any model which lives on the left side of the diagram? Like you put red and blue triangles on the right diagram.
Yes.
Right. But on the left you didn't put anything. So
because I think that so tell me if I'm wrong or not, but I mean I take a model, right? I play around with my model without changing the symmetries. I change some things a bit, and I can change a lot the phase the nature of the phase transition. Yeah. That should sort of ring bells that there's something maybe not like this, right? Would you agree? Because this is unless you
consider yet models on that half.
Yeah, all right. I don't know. So I don't know where to put it. I don't really know where to put it here, right? To put it here, I suppose that the short range would be like that. It would flow to this SO5 point. The long range somehow would sort of cross this line and then go here, right? But that I think would be maybe. Right?
I mean, the thing about the thing on the left is then it's difficult to explain. If you assume this scenario on the left, it's hard to explain why many different models all seem to show some close to critical behavior.
Right.
And even if you assume that you can't access the thing on the left because of it requires a sign problem or something, you still don't have a natural explanation of why you happen to, in all these models, be close to that.
Yeah, but you agree that even if you think about this way with the walking, it is somehow surprising that why don't we have more models on this side?
Because you don't report those models. Right?
So this is psychology of science, right? Okay, so this is the truth? Okay. So there are many models which have the same symmetry and you tune something and which are? Which are? Tell me which are. I mean, I don't...
in your model, right, in certain parameter regime, you have to often work hard to get there.
You have to work hard to get there. I mean, I don't know so many... So my experience is the following, is that I mean, there were models where we had strong first order transitions for obvious reason. That was, for example, Wei's talk on the monopoles, right? We have a hexagonal lattice, bang, it goes very strongly first order. That's trivial to a certain extent, right? But if I don't change the symmetries, this is the first model I can somehow tune a parameter and have the impression I can go from something weakly first order to strongly first order. For me, that's new.
Yeah, I think Anders also.
That's a JQ. I was saying this. That's a JQ with a discrete, but that is an imaginary time, and this is totally in agreement with what Anders has, but with but with in real space, right? That's the same thing. Essentially.
You have the SO5 order parameter, so if you just put longer range interactions by hand for this SO5 order parameter, you'll be far on the right way.
Yeah. So what we're doing, a possible plan is to put in those phonons in these monopole-free models, right? So we can do that using the same trick and putting in some phonons in this monopole-free models. It's easier for us to change the range of the interaction in imaginary time than in real space. That's all. But it's the same thing, right? And so put that into this monopole-free and then tune things. And I believe this gives me some. This at least gives me some level of, sort of, it's easier for me to understand these results in terms of such a flow or the tricritical point. Not in terms of
But one big difference between what Anders did and what other people can do is that Anders, his collaborators, they claim that they actually see this power law. That they vary and they see power law.
Yes, I can agree.
While other people either didn't vary, and so they didn't see a power law, but maybe if they varied, they would also see it. And if they see the power law, then
so we could try
basically inconsistent with this working scenario.
Right.
Power law is inconsistent with the working scenario.
Right. So what I agree. So the power law means the plot that Anders you had of the basically the order parameter as a function of your Q. You had a couple of points, and then it went to 0 in your sign fold part of the diagram. That's the one. That's the one you're talking about. Yeah.
Well, but we also see power laws, in correlation functions and so on up to.
So one could try.
No, but power laws in correlation. I'm talking about power law in the order parameter.
Yeah.
I think power law in the order parameter is if it's actually confirmed, then I think it excludes working scenario.
It excludes this.
It excludes
this-
walking. The power law in order parameter excludes walking. So, for example, Adam, as I understand, in your loop model, you never tried to vary the model a bit and see this power law, or maybe you couldn't see that. So this is really.
But I mean,
But you could vary your model and try to go or not.
but all the models have, they have indistinguishably small values of the order parameter.
Well, you
even
can
in
go
the walking
for-
style.
because you can go-
Others, it was not indistinguishably small.
Oh, it was very small.
He has error bars, which are way smaller than the actual
It was,
zero
it
value. that
was,
he claims.
it was pretty small.
But the error bars were even smaller.
Yeah, but that's Anders.
Who's had the best simulation, so we can't.
But I think the loop model and the JQ model, they give very consistent results, right? Adam, there's no conflict between those, I think.
Yeah, I haven't followed the recent stuff.
Can I just have a quick question? Go back to the SSH model. I mean, can you put it up? So it has an exact SO5 symmetry.
No. This has no exact SO5. This has no symmetry.
Just very quickly, why isn't it a superconductor?
Oh.
Can you make it a superconductor?
So the O4 symmetry tells you that the spin and the superconductors are degenerate.
Okay.
Right. So this is, if you want to be very clear, the AFM coincides with a CDW and an S-wave superconductor. Right. And so that's why we decided to put in a Hubbard U term to get rid of this.
You do have a Hubbard.
We put in, not here, not in the first part, but we checked that everything we do here is putting in a Hubbard U term to get away from this O4 symmetry, which is a bit tricky.
What I think would be great to do, find a way to make it a D-wave superconductor.
Yeah, I imagine, right? Good.
Okay,
Yeah.
we can talk about
Okay, good.
I guess we should wrap on it. Ouch. So let's take the speed again.